entropy and enthalpy are related in the sense that we're talking about dispersion with both. So in the enthalpy, we were saying that reactions were likely to happen when they were exothermic, so heat was being dispersed. We're also saying when the particles spread out, when they become gaseous, they're spreading out. When a solid becomes dissolved, they're spreading out. The matter is being dispersed. So both of these things are driving factors for reactions. And we have to look at both of them to figure out if a reaction will occur. So exothermic reactions tend to occur, it's dispersion of heat. Reactions where entropy increases tends to occur because it's dispersion of matter. And there's one equation that's going to tie both of these together, and it's Gibbs energy, or one variable that's going to tie these things together, and it's Gibbs free energy. Gibbs free energy is the energy from a reaction available to do work. So that's looking at how much heat was released minus how much of that energy was required to move the particles, because you know it takes work to move the particles. So there we go. And this is the equation. Gibbs, G finally, yay. G stands for Gibbs. We have the Gibbs of a reaction, change of Gibbs in a reaction will be equal to the change of enthalpy minus the temperature times the change in entropy of the reaction. And there we see that entropy is based on temperature. So Gibbs will tell us, Gibbs is the one thing that will always tell us if a reaction will occur spontaneously, which means it happens. It doesn't mean it happens fast. It just means that it will happen. So spontaneously at certain conditions. Kinetics will tell us if a reaction happens quickly. For example, graphite spontaneously turns into diamond. Oops, sorry, other way around. Diamond spontaneously turns into graphite. But that doesn't mean in a second it's going to happen. The spontaneous is going to happen over many, many years, so you don't really have to worry about your diamonds. So don't worry if you were worrying about your diamonds. So here's an example. We're looking at enthalpy and entropy. 50 kilojoules are released as heat, and 20 joules are going to be required due to the entropy decreasing. The overall Gibbs energy would be, unfortunately notice I used 50 kilojoules here and 20 joules here. So it's really going to be 50 kilojoules minus, this is going to be 0.020. With sig figs, I can go ahead and say that I don't really know these places, so it stays about 50. So very little of my heat was, or little of my heat was used to move the particles around. So we still have kilojoules. So watch your signs, watch your positives and negatives, and make sure you watch your units even more so, because the enthalpy is going to be in kilojoules per mole, the entropy is going to be in joules per mole. And had I not noticed, I would have said the change was 30. And that's slightly different. Okay. Let's go ahead and actually calculate one, or actually see some conditions. So here's different conditions. We said we have to look at enthalpy and entropy to figure out if a reaction is going to spontaneously occur. I should tell you that the signs that are favored for all of these, we want exothermic reactions. We want entropy to increase. And I'm saying want just because we're looking for spontaneous reactions. I don't really have any emotional preference for either. So for a reaction to be spontaneous, this was a factor that would contribute to the spontaneity. This is a factor that would contribute, and this is what tells me. This is the thing that says, yes, it will happen. If your Gibbs is negative, this reaction is spontaneous. So here I have unfavored. I have an unfavored enthalpy and a favored entropy. Okay, so in the end, it means I've got one factor detracting from this reaction happening and one leading it to happen. I don't know if it's going to happen. I know it'll happen under some conditions and not others. So to look at this, I know this is going to be against this reaction happening. This will be for the reaction happening. And the times that it actually will happen are when this factor is more important. So when temperature is high, it makes this factor more important than this factor. And then the Gibbs will end up being negative because you'll have minus a very large number right here. So this is going to be negative at high temps. And does it occur at high temperatures? No, we have negative, negative. So now the enthalpy is favored, because it's exothermic, but the entropy is unfavored. Okay, because it's a negative change. So it's the exact opposite. We need this factor to be unimportant for this to occur. Meaning we need, if this is going to be negative, negative times negative makes this part positive. We need a negative Gibbs for this reaction to be spontaneous. So we want this to be more important than that. That means this reaction will occur when temps are very small. So at low temps. So you'll have a negative Gibbs at low temps. That means this reaction will occur at low temperatures. Now imagine you have a reaction where the enthalpy is positive. That's unfavored. And the entropy has a negative change. That's also unfavored. This one is much easier. Neither one of these is favored, so no, this reaction is not spontaneous. So it's going to have a positive Gibbs. No, it's not spontaneous. And what if we have a reaction that's going to have negative enthalpy? That's exothermic, so it's favored. And we have a positive change in entropy, also favored. If you have a negative thing minus something times a negative thing, sorry, something times a positive thing, then we have negative here, your Gibbs is negative. That means yes. That is a spontaneous reaction at high temps and low temps. And we can also calculate with Gibbs. So here we have, we're going to calculate the standard Gibbs energy, and as we talked about, Gibbs is the energy that's available to do work, and standard is going to be, we're at standard conditions, we're at 298 Kelvin and 1 atmosphere. So I'm going to use this equation. And when we saw that the Gibbs free energy is equal to the change of enthalpy minus temperature times delta S. So my enthalpy of reaction is negative 571.6 kilojoules per mole. And I'm subtracting from that T delta S. We said standard conditions, so that's 298 Kelvin times the entropy. I have kilojoules here, and I'm almost always using kilojoules per mole for my Gibbs as well. So I'm going to convert this joules per mole to kilojoules per mole. So since there's 1,000 joules in kilojoule, I'll just move the decimal by divided by 1,000. So I have negative 0.3266 joules per mole. That actually is joule per mole Kelvin. I left off the Kelvin in the unit. The units for entropy will always be joules per mole Kelvin. So there. And that Kelvin shows up right here. Let me cross that out. Okay. So then I have, oops, we said we were changing kilojoules. We have this amount will be positive, added to that, and so my delta Gibbs for this reaction is going to be a negative 474.25 kilojoules per mole. There is actually a second way to find this as well that would have been a little bit faster. So this Gibbs is actually, if you noticed, I have hydrogen, an element, in its standard state at standard conditions, and I have oxygen in its standard state under standard conditions. Those are two elements making, this is 2 moles of a compound. So actually the delta Gibbs for this reaction is going to be twice the Gibbs of formation. Gibbs of formation is going to be the same as enthalpies of formation, but now we're using Gibbs instead of enthalpy. So if I were to form 1 mole of water from its elemental parts at their standard states at standard conditions, I could look up the value for the Gibbs of formation, and that would be how much free energy is released when I make 1 mole of a compound from its elements at standard state under standard conditions. Since I'm making 2 moles, I could have just done that, but I also have this way. So now we actually have 2 ways to solve for that.